You guys a question. How do you get electricity? Huh? How do we get electricity? Well, I just paid the electric company and then boom, here's electricity. Well, okay, that's fine, but how do they get electricity? Huh?
Power.
Well, how do they get power? Well, that's the same question.
Electrical charges.
Yeah, but how do they get, but how does that happen?
Work.
Huh? Voltage? Yeah, but how do they get the voltage?
Generator?
Okay, but
They
what is in a
burn gas?
generator? Huh?
They burn gas?
They don't burn
Generator?
gas.
I don't know.
Okay, what I have here is a simplified version of what's actually happening at these electric companies. All you do is you spin this, and what happens? You get current flowing through, and then you are able to power lights. Okay. But how does that actually happen? Just because you turn something doesn't mean that there's always going to be electricity, right? So how do these things happen? And we're going to go over the answer to this. And so it doesn't matter if it's hydropower, it doesn't matter if it's wind power, it doesn't matter if it's nuclear power, all of them use this same fundamental principle. The only thing that's different, or the only source of energy that's kind of different, is solar power. Solar power doesn't use this, they have a alternate method, but wind, nuclear, what other one did I say? Wind, nuclear, water. Yeah, pretty much every other kind of a source uses this kind of fundamental mechanism. So we're going to go over how that works. Unfortunately, that's going to be the second half of class. So we got to begin, we eventually have to make our way there. Okay, so last class we talked about the strange interactions charges and magnetic fields have and some applications that exist therein. This time we're going to take a step back and be a little bit more fundamental. So we want to begin with this basic question. Where do magnetic fields come from? Where do magnetic fields come from? There's two answers to this. One of them are what are called permanent magnets. And what permanent magnets are? Who's taken chemistry? Okay, I'm sure you guys have heard of this thing called the quantum spin state. The spin state, or the magnetic spin. Something along those lines. Yeah, that arises to magnetism. So spin states of electrons, and permanent magnets are more common in elements with unpaired valence electron. Now, unfortunately, this field is extremely complex, and we don't really care about it because this class isn't talking about this because we care about the fundamentals, but we care about electricity and magnetism because of its applications. And so there's a second answer, and this is what we will be covering, and these are called electromagnets. Electromagnets. So these are not permanent magnets, but these are magnets that are generated by electricity. Darn it. Okay. Essentially, electromagnets, these are wires with current. Wires with current. And if the wires with the current are in a certain geometry, then we give it an alternate name, and that is called a solenoid. That is called a solenoid. So wires generate a magnetic field, right? Wires generate magnetic fields. And so for a single wire, we have this expression. B is equal to mu naught over 2 pi times I over R, where I is defined as the current, R is the distance, and this mu naught, this is kind of the epsilon naught. Do you guys remember that? The permittivity of empty space? Mu naught is the permeability of free space. So permittivity was how space itself interacts with electricity or charges. Permeability is how space interacts with magnetic poles, magnetism. So magnetic fields are vectors. This only gives us the magnitude. For the direction, use the right-hand rule. And just as a reminder, if we have a current in this direction, the generated magnetic field, we take out our right hand, thumb goes in the direction of the current, and the curl of your fingers is the direction of the magnetic field. So we have this, that. So above the wire, the magnetic field is coming towards us, so it looks like this. Below the magnetic field, it's going back into the page, so it looks like this. So wire generates a magnetic field as such. Now with that, let's do a few different examples. Let's say you have 4 wires with current I in or out of page. Question is, in which configuration is the magnetic field B greatest at the center? So we're going to have 2 different configurations. Let's say call this configuration 1. Here's wire 1, wire 2, wire 3, and wire 4. And in configuration A, wires 1 and 2 are coming going into the page. Wires 3 and 4 are coming out of the page. Whereas in scenario B, the wires are the same, so they are located with the same distance and everything. You're just changing the direction that the current is flowing. That's wire 1, 2, 3, and 4. This time, wires 1 and 4 are into the page. Wires 2 and 3 are coming out of the page. And we want to know, from these 4 wires, what is the magnetic field right at the center? That is the question. So here, we take out our right hand. Current's going into the page for current 1. The curl of our fingers is going to be the magnetic field of 1, so it's like this. However, we don't care about it just right around it. We care about how wire 1 interacts with the center. So what we need to do is draw for ourselves circle that with the wire 1 at the radius, and the magnetic field is going to be tangent to that circle. And it's going in the counterclockwise, or this is a clockwise direction. It's going clockwise because of the right-hand rule. We do the same thing for wire number 2. It's going into the page, so magnetic field is going to be clockwise. And like we did the same, we want to find a circle with radius 2, with wire 2 at the center. So it's going to look like this. And the magnetic field is going to be tangent to the circle going clockwise. So this is going to be magnetic field V2. For wire 3, current's coming out of the page, so the magnetic field is going to be counterclockwise. So like we did before, we find our circle where wire 3 is at the center. And in this case, the magnetic field is counterclockwise, that is tangent, and so you see it is going in the same direction as V2. That is V2. We're doing the same thing for wire number 4. We find the circle that wire 4 is at the center of. Wire 4 is coming out, so the magnetic field is counterclockwise, and so it will look like the following. Now let's draw this scenario without some of the complexity. So here we would have wire 1, wire 2, wire 3, wire 4. At the center, what we're going to have is B2, B3, B1, and B4. That's what it's going to look like. So what would the net magnetic field at the center be? What would the net magnetic field at the center be?
Would be to the left.
So it would be simply to the left. This would be B net. Now we do the same analysis for configuration B. Notice the locations of wires 1 and 3 are the same. So we can begin by drawing those. Wire 1 is going to have a magnetic field in this direction, this is B1. And this is magnetic field B3. Now we just need to do this for wires 2 and 3. So we begin by drawing the circle. Wire 2 up, so it's going to be this way. So we're drawing the magnetic field is tangent to the circle in the counterclockwise direction, so this is B2. Wire number 4. Find your circle. Going into the page, so the magnetic field is going to be clockwise. Tangent to the circle means it's this direction. So what is the net magnetic field in scenario B?
0.
Yeah, B3 cancels with B2, B1 cancels with B4. So the net magnetic field is 0. Are we finished? Well, the answer is no, because I asked you for which configuration. So you would say, therefore, A has greater Let's do another example. And we want to look at what is the force between two parallel wires. So let's say we have these two wires, they're parallel, and let's say both currents are going in this direction. Well, first, let's understand why we would even expect there to be a force between the two wires in the first place. First thing we have to understand is wires generate a magnetic field, right? We just went over this right here. So wires are generating a magnetic field in this fashion. So wire 1, if you use the right-hand rule, this is going to be the magnetic field. So on the left-hand side, it's coming out, and on the right-hand side, it's going in. But wire 1 isn't just generating a magnetic field immediately around it, it's also generating a magnetic field that will eventually interact with wire I2. And one of the things that we discussed is a wire in the presence of a magnetic field experiences a force. So let's write that into bullet points. So here, wire 1 generates a magnetic field B1, and it is the magnetic field B1 which interacts with I2. So the wires aren't actually touching, but wire 1 generates a magnetic field which will then result in a force on wire 2. Well, right now the scenario is not complete because wire 2 is also a wire which generates a magnetic field. So wire 2 is generating a magnetic field in this fashion. So wire 2 is also generating a field wire 2 generates B2, and it is B2 that interacts with I1. So when we're talking about what is the force between two parallel wires, we have two forces that we need to find. There's going to be a force, we'll call it that interacts with I2. This would be force 1, 2. Wire 2 generates B2 and interacts with B1. That is force which we would call 2, 1. We have two different forces for two parallel wires. Now I think at the beginning of last week, or last lecture, I gave you this expression. Force of a wire is IL cross B. Oh, I forgot to mention, let's say these two wires are spaced a d distance apart. Let's call this wire 1 and wire 2. So the force, let's just do F1 on 2, is going to be equal to I LB sine of theta. Except it's not. Because we need to be precise about what these index actually refers to. So here, the force of the wire is equal to the current of the wire times L cross the magnetic field B. This is the external magnetic field. So F12 is going to be equal to, is this I1 or I2?
1.
Who says 1? Raise your hand. Fortunately, you're incorrect. This is 2. Because the second object is on the receiving end. This is the force of the receiving wire is the current of the receiving wire times L cross B. So this is of the wire that's on the receiving end. And this is the second index, so this is force of 1 on 2. 2 is on the receiving end. So likewise, this is the length of 2. But what about the magnetic field? What index will we give it? What subscript? 1 is correct because it is the wire 1 that's generating the magnetic field wire 2 is experiencing. Also, what is theta? Here, theta is the angle between the wire and the magnetic field. I2, the L is up, right? Because that's the direction of the current. What about the magnetic field from wire 1? Here, it's going into the page. Right? Do you see these into the pages? Into the pages? What's the angle between up and into the page? Right, it's 90, so sine of 90 is 1. Sine of 90 is 1. Well, what is B1? Well, I just introduced an expression to you that gives you what the magnetic field is resulting from a current. And so that is mu naught over 2 pi times I over the distance, which is d. But which current is this? Which I is that?
I1.
Are you sure?
No.
2.
Are you sure?
No, 1. It's 1.
It is 1 because it is the current 1 that's generating the corresponding magnetic field. So this time it is I1. So putting these two together, we get F12 is equal to I2 L2 times B1, which is mu naught I1 2 pi over d. Are we finished? Why not? Yes, now we only got one of the forces, we need the other. So we got to do F2 on 1. What's going to be the subscript? This is going to be equal to I, which subscript? It's I1, L, 1, B, 2 and sine of theta, but we already discussed that the angle is already 90 degrees, so that's 1. And here, B2 is going to be mu naught over 2 pi times the current, but which current? Current from which wire? And it is 2. And what is the distance? It is lowercase d. So then F21 is going to be I1 L1 times mu naught I2 over 2 pi. Now are we finished?
No.
That's correct. What's missing? Alright, so we are done.
No.
We're not done?
You have to find,
We're not done?
you gotta find the force between them still.
This is the force between, oh, but this is not.
Yeah, there it is. Now we're done.
Alright, now are we done?
Extra credit point.
Yeah, now are we done? No, we're still not done! Oh, what are we missing?
Take the difference.
Huh?
Take the difference.
No, not the difference.
Oh.
You have to combine them.
Huh?
You have to combine them.
No.
Oh.
No. Force is a vector. We only found the magnitude. What direction are these forces? For that,
Right.
we have to use the right hand rule. Force is IL cross B. So let's look at, this is going to be F1 on 2. L cross B, the direction of the magnetic field is into the page, so the middle finger is going into the page. Our thumb is going to the side. This is F1, 2. What about F21? The current's going up. The magnetic field, B2, all the way over here. So here, this is the magnetic field. So the dots are on this side. It's coming out of the page on this side. And this is exactly where wire 1 is. So it's L cross B, and the thumb is pointing inward. So this is F21. So two parallel wires are having attractive forces onto each other. Now, some of you guys might have a little bit of a problem accepting this, because I'm sure you guys have played with wires that were, that had current flowing through them, but you didn't see any meaningful forces in between them, right? How often when you plug stuff in, do the wires magically clump together? Pretty much never. Part of the reason is you guys are using much smaller current to actually generate enough force. Another reason is that it's not in the proper geometry. A single wire, yes, does not generate enough magnetic field so that you can actually observe these attractive forces. And so there is what is called a solenoid, which is intended to amplify this magnetic effect. What this solenoid is simply the correct geometry for getting large magnetic fields. Correct geometry for a wire. So what do you do with a wire? A solenoid is simply a wire coiled into a helix. A wire coiled into a helix. Or a spring, just think of a spring. So a simplified sketch would be something that looks like this. So here a current would be flowing like this and a flowing like that. This helical geometry is going to have a large magnetic field at the center, or inside this, inside the helix. So has large B inside the helix. It has a large magnetic field inside the helix. A solenoid is sometimes given a more common name called a electromagnet. Although I don't think a solenoid is the only geometry for an electromagnet, but most of the time, or at least the most common ones, it is a solenoid. So electromagnetics and solenoids are kind of one and the same thing. To understand this, let's cut this in half and look at the 2D standpoint. So let's cut it in half. So we have wires at the top and wires at the bottom. So here my coil is going up into the page, out of the page, into the page, out of the page. So at the top, they are all into the page. And at the bottom, the currents are all out of the page. So if a current is generated, these individual coils are going to generate a magnetic field. This is going into the page, so what are the individual magnetic fields going to be? The right-hand rule tells us it is going to be in the clockwise direction. That one is that one is that. One is that. One is that. So it's going into the page, and then the current at the bottom is coming out of the page. And so the current, using our right-hand rule, is going to be in this direction. But these wires, they're all, or these points of the wire, they're not just generating a magnetic field immediately around it, but it's all throughout it. So once this, the cumulative effect of this, and this is towards the top, you're going to get a magnetic field in that direction. The cumulative effect of the wires on the bottom is going to be this direction. There you go. This is going to be the magnetic field of a solenoid. So let's go over the mathematical relationship. The magnetic field of a solenoid is given by this expression, mu naught Ni over L. Where L is defined, so here, this would be the length of the solenoid L. Here N is the number of turns, and I is defined as the current. And so within this helix, what you're having is a magnetic field that looks like this. Well, here's the thing. If you continue this, it will look will pretty much look identical to as if you had a permanent magnet right here with the north and the south. So the solenoid pretty much behaves as a permanent magnet. So remember the magnetic field lines from the north to the south magnets that we drew? Yes, the solenoid essentially looks like that, or generates those type of magnetic field lines outside of the solenoid. And you have a very centralized, high magnitude magnetic field within the center of the helix. So, here with this, we see that we can amplify. Here's the thing. Electromagnets are much, much stronger than permanent magnets. Because electromagnetics, you can increase a magnetic field very, very easily. One is by changing the current. So we can amplify B by increasing the current I. What is another way that we can amplify the current? Amplify the magnitude of the magnetic field?
Increase the number of coils.
Yeah. This simply just make more coils. Oh, it's not strong enough? Alright, just loop it more times. And then you'll get a stronger magnetic field. Now, unfortunately, this is the lab that kind of got canceled. Although I'm thinking, I heard a lot of sighs from the first section, so I might just do a very shortened version of it, but we'll see. But yeah, so you guys would have been making your own electromagnets in the lab. But potentially that's the lab that's getting canceled. Any questions on that stuff so far? Okay. Now we can get onto this stuff. Getting to the heart of how that works. And so I think this is section 3B or something along those lines. And I'm going to call this section induction and what is called Faraday's law. Induction and Faraday's law. So let's kind of go over the broad observations that we've been making so far. So thus far, one, we saw that current produces a magnetic field B. So current produces a magnetic field B. Second, B, a magnetic field, exerts force on current I. So we made these two observational notes so far. Current produces a magnetic field, and also the magnetic fields exert a force on a current. So we see this intimate relationship between the current and magnetic field, between charges and poles. However, we really don't care if a current can produce B as much as, for us, we want to see what can generate a current. Because magnetic fields, they're not too entirely useful. Although they are, but we'll kind of get to some of those other applications. But current can actually lead to the use of all these electrical devices that we are very fond of in our technological age. So we care about current. So we see that current and magnetic field are related, so naturally, if I can produce B, might B be able to produce the current I? So if I produces B, and we see that magnetic fields and currents are related, then do they also have this relationship? Can B produce a current I? Remember, the electrical current is how all of these electrical devices work. This, the production of I, is what we so dearly care about. And the answer is no. Except kind of. Except kind of it can. Because this question is actually a complex question. There's a few different parts. And it's because there's a subtle nuance that we must visit. The first one is that a constant magnetic field B does not produce a constant magnetic field does not produce a current. And so that's why the answer is no, except it's kind of, because a changing magnetic field B does produce current. That's why it's kind of. The magnetic field itself doesn't, but if it's changing, then it can produce a current. And the current that is resulting from a changing magnetic field B, this is what is defined as induced current. It's defined as the induced current. And this leads us to this guy named Michael Faraday. So Faraday observed the following. Oh, I forgot to mention. So a changing B induces an EMF, or the epsilon, or the voltage. So changing magnetic field induces a voltage, essentially acts as a battery, and we know that batteries end up generating a current if it's hooked up to a circuit. And so that's the full cause and effect sequence. And this is what Faraday observed. He observed the following. The electromotive force epsilon is equal to negative N times delta phi or phi over delta t. Where here n defined as the number of loops and phi b is what is called the magnetic flux. So if you guys remember Gauss's law, we dealt with the electric flux. This time it is the magnetic flux. Where phi b is simply b dot a. So this is dealing with the amount of flux that's passing through some area A. So a changing magnetic field induces an electromotive force, or a changing magnetic field eventually produces a current. However, there should be a glaring question, and that is, which direction does the current flow? Which direction does a current flow? And the answer is an induced EMF is in the direction that opposes the original change in flux that caused it. Well, that's a lot of words, so let me just simplify the idea. Let me just give you one word. Resistance. It applies resistance. It applies, oh, sorry, not resistance, I meant resistive. Resistance is too close to the electricity term. It is resistive. Now, what does that mean? So let's look at a scenario. Let's say we have a wire with one loop. And here we have a bar magnet, north and a south. The bar magnet has a magnetic field which is going up. Now, when we place a magnet on the wire or near proximity of the wire, there is no current because right now the magnet's going to be applying a constant magnetic field to the wire. However, what we're going to be doing is taking this magnet and we're going to be moving it through the wire. We're going to take the magnet, shove it through the wire, because as the wire's getting closer, the magnetic field, it's distance dependent. As the distance is getting closer, the magnetic field is increasing. Magnetic field is increasing. So, there's going to be a current generated in the wire that's going to try to stop the magnet from going up. Instead, the magnetic field, the resulting magnetic field, is going to try to push the magnet back down. That's what it means to be resistive. So, instead of having a upward, so what the current's going to want to do is it wants to generate a magnetic field. It wants to induce a magnetic field down onto the magnet. Down onto the magnet. But which direction is the current going to flow to actually do this? To find out the answer, you take out your which hand? The right hand. We have a current, which is in the thumb. The curl of the fingers is the induced, or is the magnetic field. Normally, we have the direction of the current and we're trying to find the magnetic field. This time it's reversed. We have the magnetic field and we want to know what the direction of that current is. So, from, let's say, this portion of the wire here, to generate a magnetic field down, we know that the curl of the fingers has to be into the page, so the direction of the current is that direction. So the current is that direction. Making sure that we're doing it correctly, let's follow it from the top of the wire here to generate a magnetic field down. The curl of the fingers has to be this way. So the thumb, okay, I'm not tall enough, but our thumb has to be pointing that direction, so the current is this way. And that is consistent. If we follow the flow of the wire, it does that. And so if we take the magnet with the north up and we begin to move it up, then we're going to generate a current flowing through it this way. So that's what it means to be resistive. So whatever the change in the flux is, it's going to try to oppose it. This is what is called Lenz's law. And here's the thing. You guys already observed this effect in one of the labs. Which lab? You remember your bloody fingers?
Oh, the magnet.
The magnets! Remember what happened when you dropped the magnet into the copper tube? What happened?
So it's
The magnet slowed down. Why did it slow down? It's because in that copper tube, electrons begin to flow, which generates a magnetic field that tries to suspend it in midair. The magnet's trying to go down, and the copper tube generates a current, which is generating a magnetic field, trying to push the magnet back up. You already observed this. Also, you observed it right here. Right, this is also how that works. So let's make the full connection. Okay, this is where we'll end up. How does that work? It does rely on this principle of Lenz's law and induction. So here, the application of induction. We're going to go over generators and transformers. And I am not talking about the robots. Today we'll only have time for generators, because that's where I ended off the previous section. So one thing to recognize is AC, so alternating current, is obtained from generators. And this is the reason why electric power plants, electric companies supply alternating current to us. And so ultimately the question we really want to answer is how to get alternating current AC. And the answer is simple. That is this idea of induction, which is current generated to resist. Let's put it that way. And this is precisely what generators, or the fundamental principle that generators operate on. What they do is they take mechanical energy so in that little hand crank generator, I had to turn it. It was taking the mechanical energy that I was giving the generator, and it turns that into electrical energy. And for this, although there's many moving parts, let me just give you the essential fundamentals or fundamental parts of a generator. That is magnets, wires, and rotational motion. And that is it. These are the three essential ingredients to actually build a generator. Magnets, wires, and rotational motion. And of course, you can't just take magnets, wires, and then just start spinning it in whatever direction and expect to get out current. Of course, that's not going to happen, and this is why scientists and engineers get the expensive bucks. Because they not only know what is important, but they know how to actually arrange these different pieces in an intelligent fashion to do whatever it is that you actually want. And that's where most of the money is. It's in understanding how to put things together. So let's go over. So magnets, wires, rotational motion equals AC. So let's actually go over how that works, and then we will call it a day. So get out your drawing hands and your thinking caps, because you're going to have to do a little bit of drawing as well as visualization. So first, you're going to need the north magnet here. And this is the south magnet. So what is the direction of the magnetic field going to be? So in between these two magnets, there's going to be a north to the south. So you have a uniform magnetic field in between those two magnets. So that's magnets checked off. Now what else do we need? Wire. For the wire, okay, this is where you need your thinking caps. Visualize with me. We're going to put a wire, and we're going to kind of shape it so it looks like this. This is a single strand. I bend it, I bend it, I bend it, I bend it. Now this is kind of at an angle. Let me do a side view. The wire is going to look like this. So the wire is kind of in the shape of a spatula. Do you guys get that? So I bend it into the shape of a spatula, and I put it in between. Now normally, I want many, many different loops. However, if I were to draw those loops the picture is going to get quite complex very quickly. So instead, let's just use a single loop and understand using more loops will be much more effective. But the general principle is much easier to demonstrate using a single loop. So we talked about the magnets, we talked about the wire, and all that's left to do is rotate. But here's the thing. Remember, a changing magnetic field can produce a current. However, it's the magnetic flux. How much magnetic flux, or how much flux, is going through this wire? We can change the flux without actually changing the magnetic field. Because we can change the flux by rotating this. By moving the wire, by rotating the wire, we are changing the magnetic flux going through the wire. Even though the magnetic field remains the same, what we're doing is actually simply moving the wire. You can get the same effect by moving the outside magnet and spinning it around, that's fine. However, it is much easier to spin this wire. And that's it. This is how you get alternating current. But let's see how, okay? So you're still not convinced. I'm trying to rotate the wire which direction? Clockwise or counterclockwise? Clockwise. Remember this principle of induction. Current's going to flow to resist it. So, there's going to be an opposing force. Because I'm trying to rotate it clockwise, there's going to be an induced force trying to push me backwards. So there's going to be an induced force up on the right-hand side and down on the left-hand side, right? This is the counterclockwise motion. Yeah, question.
Why are we rotating clockwise?
Huh?
Why are you rotating clockwise?
Because I want to.
Okay.
I could easily turn it counterclockwise, but then the induced force would be the opposite.
So it doesn't really matter then.
It doesn't matter, yes.
Okay.
But I'm saying I want to rotate it clockwise.
Okay.
I convention, whatever, I just decided that's the way
Okay.
that I'm going to turn.
Alright, fair.
But if I turn this way, this principle of induction kicks in. Current's going to flow to resist the motion that I'm trying to turn it in. So, if I'm trying to turn it clockwise, there's going to be a counterclockwise force that's induced. Right? That's what it means to be resistant. Okay, now let's see, how can we get this force? Remember this expression, F is equal to IL cross B. Normally, we have the current, we have the magnetic field, and we can find the force using right-hand rule, very simple. This time, we're going to kind of flip it around. Because we know the direction of the force, what else do we know? We know the direction of the magnetic field. What we don't know is the direction of the current. But we could still use the right-hand rule. So the force is the thumb. The magnetic field is the middle finger. Okay, so force up. The magnetic field B, that's to the right. So I need to turn my hand around so that the magnetic field, the middle finger, is this way, right? That means the current is coming towards us. On the right-hand branch, the current is going this way. The current is flowing this way. This is I induced. If the current flows this way, I cross B is the force up, which works, right? I cross B is a force up. What about on this other side? We want the force to be down. The magnetic field B, that's the middle finger, goes to the right, and the current is going into the page. So it is going into the page, and so it is going into the page. And this is I induced. And you see there is a uniform current. It goes in this way and out the other side. So that's the direction of the current. But right now, it's not alternating. But here's the thing. This is a still picture. Remember, we're rotating. What happens when we rotate 180 degrees? What was on the right-hand side ends up on the left-hand side. So right now, we actually need to tag, let's say, this side. So let's draw this portion thicker and follow along after roughly a 180-degree rotation. After a 180-degree rotation, what are you going to have? The north and the south, those still remain, they are unchanged. But what we're going to have is when we have this wire, where's the thick side going to be now?
Left.
This time it's going to be on the left. And so let's also draw this depiction down here as well. This time it's going to be like this. But remember, this thick portion on the left and the thick portion on the right, they are actually the same piece. Guess what? I'm still rotating clockwise. I'm still rotating in that direction, right? In my hand crank, the rotation that I was giving it is always one direction. If I'm still rotating it clockwise, the direction of the induced force is going to be which direction? It's going to resist it, so the force, the F induced, is still that, as well as that. The induced force is still going to try to get the wire to rotate counterclockwise. Well, how do you get an upward force and the magnetic field is still this way? Well, right-hand rule again. We know the thumb, that's up. Magnetic field is to that direction, so the current is going into the page, so the current is this way, and the current is that way. Likewise, on the left-hand side, the current is this way. And so this is how you get alternating current. Look at what's happening on the, let's just focus on the thick branch. Half of the rotation, the current's going out of the page. The other half of the rotation, the current's going in. So half rotation out, half rotation in, half rotation out, half rotation in. So this plus that is equal to alternating current. So here we could put it this way. The current is positive, and we can just denote, out would be positive. So in this rotation, or in this half of the rotation, you would have positive current. On the other half, you would have that current. And so all you need is a loop of wire, and you just spin that loop within a magnet. So let's come back and look at this. I'm going to turn it to the side. What does this outer bar look like? It is a U magnet. And inside, it's hard to see because there's some casings, but down at this thing that's rotating, there's just a bunch of wires coiled up, and that's why when I rotate it, I'm generating current. And you see that it's constantly pulsating in terms of brightness, right? And that's because, remember, we talked about power does this. for a light bulb, there's a threshold power you actually have to hit for the brightness to actually turn on. Because at a low enough point, it's not going to be hot enough to the point where it burns. So it turns on and then it turns off. And then it turns on and then it turns off, and that's what we're seeing with this right here. So this is getting alternating current. Magnet, wire, rotation, this is all you need, and here's a full explanation behind it. Except it's not, because I have a question for you guys. Well, when this is moving or rotating, you're gonna get entanglements. When we're constantly turning the wire, aren't you gonna get entanglements? And the answer is no. Okay, so let me show you how to actually fully extract the current. There's what's called brushes. Okay, it's not what you think. Ultimately, it's simply a hollow cylinder that is conducting material. It is hollow, it's just a cylindrical shell with the ends open. So you have a brush here. And one of these wires is going to be in contact with this one throughout the whole time. Even though we rotate it, so from the side view, the wire is going to be in contact here. As we're rotating it, it's simply just moving in this circle. So do you see how it's constantly in contact with the shell? That's what it's doing. For this other one, we want to jump past it, and so we kind of push it through. And so this other wire from the side view, we're just putting it here and making sure it comes out. And we attach it to a second brush, as such. And so if we rotate this thick wire is constantly in contact with the first brush, the thin part is in contact with this brush, and it's these conducting brushes that are hooked up to, let's say, the light bulb that I have. And so it is through here where the current is, you're getting AC. And so you need these metallic brushes to actually get the full thing together. All right, and that's how the Industrial Revolution #2, which historians say was the more important industrial revolution, that's how it all got started. This simple thing applied, and then now we're able to power pretty much everything. All right, well, next Monday, class is canceled. Next Wednesday, I'm not here. Neither next Thursday. So I will see you, if I'm still alive, I guess. Because it's a long time. It's a joke. Hopefully I'm still young enough to actually walk around. No. I'm just traveling. I'm just traveling.
Creates cold water.
Hold on. So all the bulb does prevents the wires from getting tangled up.
All the what?
All the bulb does prevents the wires from getting
Oh,
tangled
these
up.
are brushes.
Sorry, brushes.
Yeah.
Okay.
It allows, it removes the necessity of entanglement.
Okay.
And so there's friction, thank you, so there is friction between the wire and the shell. It's in contact and it's constantly just moving around like this. Yes, have a good day.
Oh, I see. So it's okay.
So it's just constantly moving around like this.
Okay, I see.